Hey guys, my name is IBM, and today I've taken the most bold step to solve 9702 paper 4s. This is May June series. The answers to these papers are entirely mine, so they may not be 100% correct, but from my teaching experience, I think they will be around 98% correct. So I'm trying to solve this just for fun and just for my students who really want to know how they progressed so that they can prepare themselves for the next year. So I will take you to the questions. So I'm going to solve a paper 4-1, I mean 4-2 and 4-1. I want to start with paper 4-1. So I'm going to solve paper 4-1 because 4-1 and 4-3 are the same. I'll only solve paper 4-1 and paper 4-2 because 4-3 and 4-1 are the same. Then on 10th, of course, today is what is the date today? Today is 8th of June 2024. So on Monday 10th, I will solve the multiple choice questions, but so far I only have paper 1, 2, which my students sat. So I will try to find paper 1, 1 and 1, 3. If they are the same, then I will only find 1, 1 and I solve them on 10th. That will be the last time I'll solve these papers. Then I'll go for a break because I will be very, very busy. So let's go to the questions without wasting time. I may take slightly more than 2 hours or less than because I may give a lot of explanations, too much calculations, and so on and so forth. So I'll not go through the instructions. I'll not go through the formula. I'll not go through the constants. I'll just go straight to page 4. So define gravitational potential at a point. Remember, the gravitational potential is the work done per unit mass in moving a mass from infinity to the point. You must have defined gravitational potential and electric potential. For electric potential, it was the work done per unit charge in moving a positive charge from infinity to the point. So this one is, for gravitation, it is a mass. So this is going to be the work done per unit mass in moving a mass from infinity to the point which is defined. So that's the work done per unit mass in moving a mass from infinity to the point. Remember, gravitational potential was represented by the letter phi, and your teacher must have showed you that gravitational potential is always negative gm over the radius, over the distance from the center r. So a satellite X of mass M orbits a planet at a constant distance 4r from the center of the planet. So small r is 4r, as shown in this figure. So we see the satellite X has its orbit, it has been labeled X, and we have the orbit of another satellite Y is labeled Y. The second satellite Y of mass twice m orbits the planet with the radius r. So they are all orbiting the same center. The gravitational potential at X due to the planet is minus phi. The planet is a uniform sphere. So if it is a uniform sphere, then this equation can apply. Explain why the gravitational potential at X is negative. So remember, the gravitational potential is always negative. Even in the formula, the minus is not optional. So why is the gravitational potential negative? First of all, potential at infinity, V at infinity is defined to be 0. Potential at infinity is defined to be 0. And of course, when I move one mass away from another mass, it's like when you are lifting a mass from the Earth's surface upwards, it gains gravitational potential energy, but we're taking it away from the Earth. So if this is the planet, and this is the small mass, When I take the small mass away, it is gaining gravitational potential energy. But remember, when it reaches infinity, it is zero. So it must have been moving through negative values by the time it reaches infinity, where gravitational potential is zero. So why is potential at x negative? So we shall simply say that potential at infinity is defined to be zero. If you have watched my videos, my topical past paper questions, these are very easy questions because I've solved similar questions many times and I've given a lot of explanation. So potential at infinity is defined to be zero. And when you move an object when you move a mass m from a point closer to the planet farther away, you are doing work against the attractive force because these two masses are supposed to be attracted. So potential at infinity is defined to be zero, and the force between the two masses is attractive. The force is always attractive. The two masses are supposed to always attract. The force is always attractive. So work is done on the two masses in moving them. Even if you are moving the smaller mass, work is done on the two masses in moving them apart. The force is always attractive. The force between two masses is always attractive. So when you try to move the masses apart, you're going to do work on the masses. If you bring the masses together, then they are losing work. Work is got out of the work. When you move a mass close to the Earth's surface, you are moving work from the mass. That's why the gravitational potential energy decreases. But when you take a mass away from the Earth's surface, you are adding work onto that mass. That's why gravitational potential energy increases. So work is done on the two masses in moving them apart. So that means if at infinity it is zero, and yet work is done on moving the masses apart towards infinity, then the work must that means that this means that we have been moving through negative values by the time we reach zero, or by the time we gain zero at infinity. Okay, state an expression in terms of phi for the gravitational potential at y due to the planet. They've already told us that gravitational potential at x, phi at x, is given as negative phi. Okay, but remember phi, we have already said phi is negative g m over r. We've already said that phi at x is going to be negative g times capital M. Then the distance of x from the center is 4r. So where there is small r, I'll put 4r. I'm using phi equals to negative g m over r. That is the expression for gravitational potential. So remember, this is going to be negative phi. So it means that negative phi is the same as negative g m over 4r. Okay, so that is the gravitational potential at x due to the planet is negative phi. So negative phi is the same as that, which means I would simply say that phi is the same as g m over 4r. So I want to find an expression in terms of phi for potential at y. Then I'll use phi y So phi at y is going to be negative g, capital M, mass of the planet, over the distance. Y is a distance of r from the center. Now I'm not using what was the mass of the planet? A satellite mass that orbits a planet at a constant distance. So this capital M is mass of a planet. It should not confuse us at all. This is mass of the planet, not mass of any of these. So that is mass of the planet. So this is going to be negative gm over mp, gmp over the distance of y from the center, which is just r. So this is r. So we have to combine these two equations. So we shall combine these two equations. Remember, negative phi is going to be negative gmp over r, but if I come back here, when I take a 4 the other side, I notice that 4 times phi is the same as gmp divided by r. So where there is gmp over r, I'm just going to put there 4 phi. So it means phi at y is going to be negative, where there is gmp over r, I'll put there negative 4 times phi. So our answer here is going to be negative 4 times phi. So that is a simple algebra. Remember, mp must be the mass of the planet. It's not the mass of any of these, because the gravitational potential at a point will depend on the planet. The gravitational potential, because satellites, we expect the satellites to be much smaller than the planet. So the gravitational potential at that point will depend on the mass of the planet and the distance of the point we are considering from the center of the planet. So we don't use 2m, neither do we use capital M. But I am using mp to mean mass of the planet, because for all of them, they are orbiting the same center. So they're orbiting the same planet. So the answer is going to be minus 4 phi. Then complete the table 1.1 by giving expressions in terms of sum or all of m, r, and phi for the quantities indicated for each of the satellites x and y. Okay, let's start with the gravitational field strength, G. So we know that gravitational field strength is equal to capital G, the mass of the planet, divided by the square of the distance from the center of the planet. It is not depending on the mass of the satellites. So let's consider gravitational potential at x, point x. So this will be capital G, the mass of the planet, over the distance from the center to the satellite x. Let's see, orbit x is 4r. So I'll just put here 4r. So this will be 4r, but this should be squared. And when I square this gives me 1 over 16 times g, the mass of the planet, divided by r squared. But remember, we have already seen previously in our previous part of the equation, we have already seen that 4 phi is equal to, we have already seen this expression here. 4 phi is the same as gmp over r. So I'll just substitute for that. So, but we have already seen that 4 phi is the same as g, mass of the planet, over r. So the 1r remains. So it means g at position x is going to be 1 over 16 times 1r, then times 4 phi. So that is g at position x. So when I simplify this, 4 divided by 16, that is 1 over 4. So it becomes 4 times, so it becomes phi divided by 4 times r. So the gravitational field strength at x for satellite x is going to be phi divided by 4 times r. Okay, let's try to do the same for y. Gravitational field strength satellite y due to a planet on satellite y, it is going to be gy is going to be capital G, capital M. By the way, you could also put a negative because gravitational field strength is negative, since it depends on the force, and the force is always attractive. By convention, attractive forces are always are negative. So Gm, mass of the planet. We are not using the masses of the satellites because it depends on the mass of the planet. Then this is going to be divided by the distance, orbital distance for y. The orbital distance for y is just r, so this will be divided by r, but t squared, remember? So this is going to be divided by r squared. So this is the same as 1 over r times g, mass of the planet, over r, and this one alone is 4 phi. So it means g at y is going, or g at y on satellite y is going to be 1 over r times 4 phi. So this is going to be 4 phi divided by r. So I'll just put here 4 phi divided by r. Then gravitational potential. Of course, we know that gravitational potential, it is potential energy. So it is mass times the gravitational potential. So the gravitational potential energy, I'll write E potential energy is going to be equal to, of course, is negative. This one, the minus is not optional, it is compulsory. It's negative gravitational potential times the mass. So let's consider X. So gravitational potential energy at X, remember the gravitational potential energy at X is going to be the gravitational potential at X times the mass of X, which is capital M. The mass of X is capital M. So since the gravitational potential was given as just negative phi, then times the mass, which is capital M, then it means our gravitational potential energy at X is negative phi times M. So this is mass. This time, this for gravitational potential is potential times the mass, or you can use a negative capital G, so it will be the mass of the planet times the small mass of the satellite divided by R. But remember, we have already seen this to be 4 phi. I mean, this was already given to be a different value. Or you could, even if you use 4 phi, you'll end up arriving at again at the same thing, negative phi times M for X. So this is going to simply be negative phi, that is the gravitational potential, then times the mass of the satellite. Okay. Then if you want to use negative g m over that, remember the distance was 4r. Let me use here small r, but it is a repetition. I'll be repeating myself. So for X, this would be negative capital G, capital M, P divided by 4 times capital R, then times the mass of the satellite, which is M, which is negative G, capital MP over R times M divided by 4. But remember, this one alone was 4 phi, so times capital M over 4. This is a repetition, so it takes us back to the same thing. So this would be just a repetition, but I will apply it on Y. So gravitational potential energy for Y. So it will also be at the negative. So it is also going to be it is going to be the potential. I will not put here negative because the negative automatically comes out because it is the potential. So it is going to be phi at Y for Y, then times the mass of Y. So phi for Y, we don't know phi for Y, so I'll just put there negative G, capital mass of the planet, then divide by R for Y, which is just capital R. Radius, the distance from the center to Y is just R. then times the mass of Y, which is twice capital M. But I want you to not forget that we have already seen that this one alone was 4 phi. So this is going to be negative 4 phi, then times 2 times M, which gives us negative 8 phi times M, or negative 8 M times phi. So the order doesn't matter. So this will be negative 8 phi times M. Okay, so that one is the question. I've taken a lot of time on this, but it's fine. State the magnitude and unit of absolute zero of temperature. Of course, absolute zero is 0 Kelvin. That is obvious. 0 Kelvin. The unit is Kelvin. The magnitude is 0. Explain why temperature measured using laboratory liquid in glass thermometer does not give measurement of thermodynamic temperature. Remember, for thermodynamic scale, it does not depend on the physical property of any substance. Yet, liquid in glass thermometer, its temperature depends on the physical, on the properties of the liquid or any particular substance which is used in the thermometer. It could be alcohol, it could be mercury. So the temperature will depend on the properties of the liquid used in the liquid in glass thermometer. Yet for the thermodynamic scale, it should not depend on any of those physical properties. So I will say the temperature measured using a liquid in glass thermometer depends on properties of the liquid. Or a particular substance, the liquid, which is not the case with thermodynamic temperature, which is not the case for the thermodynamic temperature. So the thermodynamic temperature does not depend on the physical properties of any particular substance, but the temperature measured using a liquid in glass thermometer depends on the physical properties of the liquid used, or the physical properties of a particular substance which is used for the liquid. So that means it will not measure at absolute temperature. The figure shows a simplified diagram of a type of thermometer called a platinum resistance thermometer. So we have a plastic strip, platinum. We don't need to know details about the diagram. The glass tube is immersed in the environment for which the temperature is to be determined. The resistance between terminals X and Y is measured. The figure shows the variation of the resistivity rho of the platinum with the thermodynamic temperature T. And we see it is a straight line. I can check if it goes to the 0. I think it goes to 0. Explain how the figure shows that platinum is suitable metal for use in a resistance thermometer. Of course, previous, we noticed that the resistivity from the graph is varying perfectly linearly with the temperature, which means there will be a unique value of resistivity for each different value of temperature. So it's a perfect instrument. So I'll say, it's a perfect physical property. It's a perfect thermometric property. So I'll say resistivity varies linearly with temperature, which means there is a unique value of resistivity for each different value of temperature. If the graph was to be something like this, then this would not be the platinum would not be a suitable metal for use in a resistance thermometer, because it means different values of resistivity would have the same temperature if the graph was curving somehow like that. So all values of temperature here would be having the same resistivity, so it would not be a good metal. But now that it is just a perfect straight line, indicating that the resistivity varies perfectly linearly with the temperature, then there is always a unique value of resistivity for each different value of temperature. So it would be a good metal for measuring temperature. So it would be a good metal for measuring for use in a thermometer. So just a reason why a platinum resistance thermometer is not suitable for measuring a rapidly changing temperature. Remember, a rapidly changing temperature would require something which is very sensitive. It doesn't need much time for the temperature to change. But for platinum resistance thermometer, when I look at the diagram, it's like, first of all, the glass must conduct before heat reaches the platinum wire or the platinum strip. So that means it will take some time. Yet a rapidly changing temperature takes a very short period of time to change. So the platinum resistance thermometer will not really be a very good candidate for such a measurement. So I would say the thermometer takes time to respond because it has high heat. It will have a high heat capacity because of, you can look at the glass. So I would say the thermometer takes time to respond because it has high heat capacity. What do I mean by high heat capacity? It will require a high amount of heat to cause a change in its temperature, because the heat must first travel through glass. So an energy transfer is needed for the thermometer to reach a temperature. So, and thermal energy transfer is needed. There will be need for thermal energy transfer, especially through the glass tube, and thermal energy transfer is needed for the thermometer to reach to reach the temperature, or to reach any temperature. So thermal energy transfer is needed. For some thermometers, for a thermometer which is used to measure rapidly changing temperatures, thermal energy transfer is not needed. It should be that as soon as there is a change in temperature, there is, for example, if you use a thermocouple, as soon as there is a change in temperature, it is reflected in a change in potential difference for a thermocouple. So there is no need for thermal energy transfer. If you recall a thermocouple, which has two junctions, one placed in one substance, another in a different substance, for it, there is no need for thermal energy transfer. It is just going to detect a difference in temperature between the two junctions and represent it as a voltage. But so this one can measure a rapidly changing temperature. But this one, thermal energy must travel through a gas and then it reaches the platinum wire or the platinum strip for there to be a temperature to be detected, or for the thermometer to reach a certain temperature. Suggest a type of thermometer that is suitable for measuring a rapidly changing temperature, and I've already mentioned this to be a thermocouple. It's rare to bring these questions about thermometers. I know many teachers may not have taught this. A negative temperature coefficient, that means a negative gradient, may be used as a type of resistance thermometer. It is a thermistor. A thermistor has its, of course, a negative temperature coefficient thermistor has its temperature decrease as resistance increase, or its resistance decrease as temperature increase. State one way in which the variation with the temperature of the resistance of a thermistor differs from that of platinum. We have seen for platinum, it is most likely going to be a straight line, but for a thermistor, we know that for a thermistor, resistance here against temperature, it is not going to be a straight line. So for a thermistor, it is nonlinear. Resistance against temperature is nonlinear. So I'll simply say for a thermistor, they have even told us it is negative coefficient, which is enough to tell us that for a thermistor, resistance decreases with increasing temperature. That's number one. Resistance decreases with increasing temperature. That's number one. For thermistor, resistance decreases with increasing temperature. That's number one. But the variation is going to be inverse. So the variation is inverse, and of course, it's going to be nonlinear. So the variation is inverse to that of platinum. So the variation is inverse, or you can say inversely proportional. And of course, it's nonlinear. You have seen this in AS electricity and nonlinear. Okay, I think that is all. Question 3, state what is meant by an ideal gas. Of course, when someone talks about an ideal gas, you should think about PV is equal to nRT, or PV is equal to nKT, where N is number of moles, or capital N is number of molecules. So a gas which obeys either this equation or this equation is going to be called an ideal gas. So I will simply say a gas which obeys, I think I will use the second one. I can also just use PV over T equals to a constant. So a gas which obeys PV over T equals to a constant where I'll just define these letters, where P is the pressure of the gas, V is the volume of the gas, and T is the absolute temperature or the thermodynamic temperature. That is temperature in Kelvin units. So you must state that this gas obeys PV over T is equal to a constant, or it obeys PV equals NKT, or it obeys PV is equal to nRT. Why am I saying PV over T is a constant? Because nR is a constant, nk is a constant. So PV over T is equal to a constant. You define the second mark, I think it will be for defining the quantities PV and T. Use one of the basic assumptions of the kinetic theory to explain what can be deduced about the potential energy associated with the random motion of molecules in an ideal gas. Potential energy. Remember, for an ideal gas, we know that the molecules are infinitely far from each other, so that the intermolecular forces are almost negligible. And if the intermolecular forces are almost negligible, then it means the potential energy is going to be zero. So I'll simply say for an ideal gas, the intermolecular forces are negligible. The intermolecular forces are negligible. I don't know the spelling of negligible, negligible, whatever it is. The intermolecular forces are negligible. There's an A here, negligible. The intermolecular forces are negligible, so potential energy is zero. So the potential, because the potential energy depends on these intermolecular forces, so the potential energy is going to be zero. So I think the first mark is mentioning that the forces are zero, or the force is zero. And the second mark should be mentioning that the potential energy is zero, because they wanted the energy. Then a sample of 0.26 meters cubed of an ideal gas is at a pressure of 2.0 times 10 to the power of 5 pascals at a temperature of 290 Kelvin. Determine the number n of molecules. So I'll just use the simplest equation. I can use PV equals to nRT, but that may take me more time. I'll just move nR and put there nk. This is the same as nk, where k is Boltzmann's constant. So I'll just make capital N the subject. N is going to be PV divided by, I'm taking this part and this part, so it is PV divided by T. So this is going to be, okay, PV divided by KT, so this is going to be 2.0 times 10 to the power of 5. The volume is 0.26. And I will divide this by 1.38, that is Boltzmann's constant, times 10 to the power of minus 23. You can check in the list of constants. Then I'll multiply this by the temperature, which is 290. So I have 2 exponent 5 times 0.26 divided by 290 times 1.38 exponent minus 23. So this is giving me 1.2999299, which is approximately 1.3. So I'll just write this as 1.3 times 10 to the power of 25. So 1.3 times 10 to the power of 25 molecules. Then the average translational kinetic energy, EK, of one molecule of the gas. So of course, if you don't know how to derive this, let me first write it here. Of course, we know that the average translational kinetic energy of a single molecule is 3 over 2 times kT. I can briefly derive it for you here. Remember, you are given this PV equals to 1 over 3 mn average C squared in the list of formula. And we have also seen that PV is equal to nkt. So I'll just simply say nkt is the same as 1 over 3 n m mean square speed. So I'm cancelling out n. And I'm multiplying both sides by a half of 3. This is 3 kt is equal to m average C squared. So multiply both sides by a half. So it will be 3 kt divided by 2 equals to a half m average C squared. So this is the average kinetic energy. You see it is in the form of a half mv squared. So the average translational kinetic energy of the molecule is 3 over 2 kt. So I'll just substitute in this formula. So this is going to be equal to 3 over 2 times 1.38 times 10 to the power of minus 23 times t, which is 290. For students who have been watching my topical videos, this is one of the easiest questions. So I'll just press my calculator. 3 divided by 2 times 290 times 1.38 exponent minus 23. So that is 6.0 times 10 to the power of minus 21. 6.0 times 10 to the power of minus 21. The internal energy of the gas, explain your reasoning. So we want to find the internal energy of the gas. Of course, by definition, if the gas is not ideal, or if the gas is ideal, we know that the potential energy is 0, but in general, we know that internal energy is going to be equal to the total kinetic energy plus potential energy of all the molecules, because it's for the whole gas of all the molecules. That is the explanation I'm giving. Internal energy is equal to the total kinetic energy plus potential energy of all the molecules. But remember, potential energy equals to 0 for an ideal gas. An ideal gas. So, or which implies that the internal energy is just going to be equal to the total kinetic energy of all the molecules. Since we already know the number of molecules and we know the kinetic energy of just one molecule, then we shall simply say this is equal to the number of molecules times the kinetic energy of one molecule. The number of molecules was it 1.3 times 10 to the power of 25, and the kinetic energy of one molecule is 6.0 times 10 to the power of minus 21. So I'll just press my calculator. 6.0 exponent minus 21 times 1.3 exponent 25. So I'm getting 7.8 times 10 to the power of 4. So 7.8 times 10 to the power of 4 joules. The volume V of the gas in B is now varied, keeping its pressure constant. So pressure is constant. On the figure, sketch the variation with the V of the internal energy U of the gas. So we have already seen that internal energy U is equal to the number of molecules times the kinetic energy. But I also want to take you back to this. Remember, PV was equal to, since they have mentioned the volume, PV is equal to a third m n mean square speed. This one is given in the list of formula. So it means 3 times PV is equal to n m mean square speed, multiplying both sides by a half. Have 3 PV over 2 equals to n times a half m mean square speed. I just wanted to show that this is EK and this is N. So it means internal energy is also equal to 3 over 2 PV, because internal energy was N times EK. And we're also seeing internal energy is 3 over 2 times PV. Remember, this is now going to be a constant. So it means internal energy is directly proportional to V, and this is going to be a perfect straight line. So I'll draw a straight line through the origin. It must be a straight line through the origin, because 3 over 2 times P is going to be constant, since they say the pressure is constant. So this is going to be a perfect line through the origin. It's a perfect straight line through the origin. The gradient is positive. The line goes through the origin. As simple as that. State what is meant by resonance. Now this is simple harmonic motion. So, of course, resonance is the oscillation of, let me just write this, the oscillation, because we already know this from my topical questions. The oscillation of an object at maximum amplitude. Of course, when an object undergoes resonance, it absorbs maximum energy and vibrates with the maximum amplitude. So the oscillation of an object at maximum amplitude. This is normally when the driving force, when the driving frequency equals to the natural frequency of the system. So whenever the driving frequency is equal to the natural frequency of the system, we say that resonance occurs, because the system absorbs maximum energy and vibrates with the maximum amplitude. So you can't forget, you must mention maximum amplitude, and you must also mention that the driving frequency is equal to the natural frequency of the system for resonance to occur. A small ball is held in place using a stretched string. One end of the string is fixed to a wall, and the other end is attached to a vibration generator as shown in the figure. Okay. So initially the vibration generator is off. So that means the vibration is natural. A student displaces the ball vertically and then releases it. The figure shows the variation of the displacement of the ball with time after it is released. So we see that it is undergoing light damping because the amplitude is gradually decreasing. You can see this from the graph. The amplitude is gradually decreasing, as you could see this from the graph. It's an exponential decrease. State the name of the phenomenon illustrated by decrease in amplitude of the oscillation. So this is going to be light damping. You can't simply say damping, that would be wrong, because there are 3 types of damping. There is critical, there is light, and there is heavy damping. But for light, critical, and heavy damping, there is no oscillation. But here they are saying the amplitude of the oscillations, decrease in the amplitude of the oscillation. So that is entirely light damping. Even from the graph, you see that is light damping. If it was critical, if you remember from my graphs, from my videos of topic of simple harmonic motion, we have heavy will take much time to reach equilibrium, but critical will take about a quarter of, if the wavelength is let me say the period is around 2 point something. A quarter of 2 point something could be somewhere here. It would take the shortest time possible to reach equilibrium for critical. This will be critical, this will be heavy. So this is light damping in a nutshell. Explain the decrease with time of the amplitude of the oscillations of the ball. So why is there a decrease? Of course, it is losing energy. And why is it losing energy? It could be due to dissipative forces that we expect, such as we can say air resistance. So I would say the oscillations of the ball lose energy. The oscillations of the ball lose energy due to dissipative forces, dissipative, or I would say resistive forces, such as air resistance, acting on the ball. Then determine the frequency of the oscillations of the ball. So frequency, of course, they have given us a graph of displacement against time. So frequency is simply the reciprocal of period, which will be 1 over. Let me find the period here. So if I start from, I'm looking for a simpler point to start from. If I start from, say, here, the complete cycle is here. So I think this is 0.25 and this is 0.5. So the time between these two intervals is 0.25. 0.5 minus 0.25, that is 0.25. So this is going to be divided by 0.25. So 1 divided by 0.25, I think this is 4. So this gives us 4 hertz or 4.0 hertz. The vibration generator in B is switched on. Now we are going to have forced oscillation. So we expect resonance to occur. And its frequency f of the vibration is gradually increased from 0 to 10. On the figure, sketch the variation with f of the amplitude of the oscillations of the ball. So this is going to be the resonance curve. The natural frequency is 4.0 Hz. The natural frequency, which we are going now to call the resonant frequency, because resonance occurs when the frequency of the vibrator is equal to the natural frequency of the ball. So f naught, or the resonant frequency, should be 4.0. So it means the amplitude is going to be maximum at 4.0. Let's look for what is the scale here. I'm looking for 4.0. The scale is 2.5 divided by 10 small squares. So that is a quarter. Each small square is a quarter. So I want to find 4. 4 divided by the answer. Those are 16 small squares. So 1, 10, 11, 12, 13, 14, 15, 16. So this is 4. 4.0. So at 4.0, we expect a maximum amplitude at 4.0. So the peak should be there. So I'll just draw a simple curve because the gradient, the amplitude is increased from 0. So I'll draw, this should have a peak at 4.0, then something like that. Okay. So you should have something like that. What is very important is that the peak should be at 4.0, around 4.0. I want to make this very clear. Okay, I think that is clear, that is enough. As long as the peak is at 0, you must have done this in class. You must have sketched the resonance curve in your class. I'm saying the peak should be at 4.0 because resonance occurs when the natural frequency is equal to the driving frequency. Okay, then question number 5, define electric field. Of course, electric field, you can find it as a region of space. Oh, by the way, before I may forget, this graph should never touch the x-axis. The curve will show a maximum amplitude at a single frequency. Let me make this sharp because I want it to show maximum amplitude at a single frequency. So I should make this very sharp. Even though it is that's not looking really very nice, but I don't know why it is not looking so nice to me. Okay, I think this would be better as long as it doesn't touch the x-axis. I'm trying to avoid having more frequencies, maximum amplitude at more than one frequencies. I want maximum amplitude to only be at, okay, I think that is fine. I want maximum amplitude to only be at 4.0. Okay, so define electric field. So I said you can find it as a region of space, but the best thing to, when someone talks about electric field, you should always be looking at electric field as force acting on a unit positive charge. So electric field is a force per unit charge acting on a positive charge. The force per unit charge acting on a positive charge. So many students would prefer to define electric field as a region of space where a force acts on a unit positive charge, or where a force is experienced by a unit positive charge. It will still give you a mark, but you must mention a positive charge and you must mention force per unit charge or force acting on a unit charge. So that is going to be the electric field, a region of space where a force is experienced by a unit positive charge or force acts on a unit positive charge. So that is the electric field. So the figure 5.1 shows two parallel conducting plates that are in a vacuum. The plates are separated by a distance of 6.7 centimeters and have a potential difference of 430 volts between them. Okay, on the figure, draw four lines. Four field lines represent the electric field between the plates. So, of course, this is a uniform electric field. So the field lines are going to be perfectly parallel and equally spaced. So I'm going to take some measurements to ensure that these field lines are equally spaced. So let me draw here my first field line. So that is 1, 2. I'm trying to ensure that I measure the distance so that they are almost equally spaced. 3, 4. So they should be equally spaced in parallel. But then field lines originate from high potential to low potential, so the arrow should point downwards. The arrows point downwards. Determine the strength E of the electric field between the plates. So we know that electric field strength is either force per unit charge or V over D. Since they have given us potential difference and separation of the plates, this will be V divided by D. V is 430, D is 6.7, so I will say 430 divided by 6.7, but I must change it to meters, so times 10 to the power of minus 2. So 430 divided by 6.7 exponent minus 2. So this is going to be 6.4 times 10 to the power of 3. 6.4 times 10 to the power of 3. So the answer here is 6.4 times 10 to the power of 3. An electron travels at a speed of 2.6 times 10 to the power of 7 towards the region between the plates as shown in the figure. On the figure, draw the path of the electron as it moves between and beyond the plate. So remember it is in a vacuum, so when it emerges, it must be emerging in a straight line. So it is an electron which is negatively charged, so it moves towards high potential. So I'm going to sketch this path vertically up, going upwards. Of course, when it emerges, I must put a ruler and draw a perfect straight line here. Let me try to increase the thickness so that I make it look better. So you must draw a smooth curve with a pencil, and when you come out of the field, then you put a ruler and draw a line, which is of course which is like a continuation but should be perfect tangent. So you can draw a better diagram than mine, but that is the path. Inside it is a curve, smooth curve. It is a smooth curve, but then when you emerge, this part here it should be straight. To get the second mark, that part there should be straight. Okay. A uniform magnetic field is now applied in the region of the electric field, so it's now a crossed field, so that the electron in B Roman 3 travels undeviated, so it should just continue. Determine the direction of the uniform magnetic field. Okay, I'm going to sketch this one here. Let's say we have the electron is coming like this, and we have seen it goes upwards initially because this is positive, this is 0. So the force due to the electric field is acting upwards. This is going to be Fe, but we want the electron to just continue in a straight line. So the force due to the magnetic field should be downwards. We want the force due to the magnetic field to be downwards. Remember, this is the electron. So I have to use Fleming's left-hand rule. I must use Fleming's left-hand rule. These two forces, of course, should be equal but opposite. Because the force due to the electric field is moving the electron upwards, the force due to the magnetic field should be acting on the electron downwards. And now from Fleming's left-hand rule, you have you pull out your left hand. I will use, let me borrow something. So I'm borrowing Fleming's left-hand rule from this side here. This is your left hand. Make sure you have placed your question paper on the table, facing away from you, or the bottom of the paper should be next to you. So using Fleming's left hand, remember we want the force to act downwards. So the thumb must by all means act downwards. So how shall I make the thumb to act downwards? Remember the particle we are considering is an electron. Fleming's left hand rule will act where the first finger is the direction of the magnetic field, the second finger will be the direction of the current, and the current flows from positive to negative. So it means the second finger points in the direction of a positive charge. But because we have an electron, it must point in the opposite direction. So the electron was moving to the right. So the second finger must point to the left because the electron is negatively charged. Yet the second finger points in the direction of the positive charge. So the only way I will make this to be possible is going to remember the thumb must point towards you because the force is pointing down the paper or towards you if the paper is on your table. So the only way I will be able to do that is by doing this. The thumb is pointing towards you because you have placed the question paper on the table. The second finger must point to the left in the opposite direction to that of the electron because the electron was coming from left to right. So the second finger must point from right to left. If I make the thumb point towards me and I make the second finger point to the left, the first finger points onto the question paper. If you are standing, you see that the first finger is pointing onto your question paper, which means the magnetic field is going to be into the paper. So the magnetic field will be into the paper using Fleming's left hand rule. So we have now agreed that the magnetic field is going to be into the paper or into the page. So I'll simply say into the page. Okay. Explain with reference to the forces exerted by the two fields on the screen why the path of the electron is undeviated. Of course, the two forces are equal but opposite. They are equal in magnitude but in opposite directions. So I'll say forces the force due to the electric field and the force due to the magnetic field are equal but opposite. So the forces are equal in magnitude and act in opposite directions on the electron. Okay, determine the flux density B of the uniform magnetic field. Give a unit with your answer. So we know that when the electron goes through undeviated, the force due to the electric field is equal to the force due to the magnetic field. So the force due to the electric field is charge times the electric field strength, and the force due to the magnetic field is given by BQ times V. So Q cancels out, and we have that B is going to be equal to E divided by V. So when I make substitutions, this is going to be what was E. I think we got E as 6.4 times 10 to the power of 3, and V is 2.6 times 10 to the power of 7. So this is 6.4 times 10 to the power of 3 divided by 2.6 times 10 to the power of 7. So 6.4 exponent 3 divided by 2.6 exponent 7. So that is 0.0002. So I'll write 2.5 times 10 to the power of 1, 2, 3, 4. So this is 2.5 times 10 to the power of minus 4. Of course, the unit of magnetic flux density is the Tesla, T, or you can write Tesla. Question 6, I think question 6 is capacitance. So the figure shows a capacitor of capacitance C connected in series with a resistor of resistance R. Initially, the switch is open. There is a PD of 12 volts across the capacitor. Okay. At time t equals to 0, the switch is closed so that there is a current I in the resistor. So if we close the switch now, the capacitor and the resistor are going to be in parallel. That means the initial PD across the capacitor is the same as the initial PD across the resistor. The figure 6.2 shows the variation of I with T. Explain the shape of the line in the figure 6.2. So we have to explain this shape here. Of course, I have already mentioned that when the switch is closed, the PD across the capacitor is the same as the PD across the resistor. That's number one. And you also remember that charge equals to C times V. That means the PD across the capacitor is proportional to the charge on the capacitor. That's number two. But of course, charge is going to decrease. Of course, charge is going to decrease with the time because we have seen the graph is going down. And we know that current in the resistor also, we know that current in the resistor from V is equal to I times R. Current in a resistor is directly proportional to the PD. Remember, the PD in the capacitor is the same as the PD across the resistor, and the PD across the capacitor is directly proportional to the charge, which charge decreases with the time. Remember, the PD across the resistor is the same as PD across the capacitor, but PD is equal to VI times R. R is constant, but V is going to decrease because the charge of the capacitor decreases, so I is going to decrease. So I'll just put this in writing. I can write as much as I want. So remember, when the switch is closed, we have a capacitor and we have a resistor. They're in parallel. So the PD across the capacitor is the same as the PD across the resistor. So I'll say with the switch closed, the PD across the capacitor is equal to the PD across the resistor. That's number one. But also remember, V is equal to Q is equal to CV. So the PD across the capacitor is proportional to the charge on. So the first one with the switch closed, PD across the capacitor is equal to PD across the resistor. Here they're in what? They're in parallel. Then the PD across the capacitor is proportional to the charge on the capacitor. I'm using Q equals to C times V. And the charge, of course, the charge on the capacitor decreases. And charge on the capacitor decreases. If the charge on the capacitor decreases, it means the PD has decreased. So it also means the PD across the resistor has decreased. So and the charge on the capacitor decreases with time. So we also know that current on the resistor is proportional to the PD across at the resistor. I'm using V equals to I times R. But of course, what is the current in the resistor? Current in the resistor is going to be equal to the rate of decrease of the charge on the capacitor. But the current in the resistor is going to be equal to the rate of decrease the rate of decrease of charge on the capacitor. So the current is in the resistor is going to be equal to the rate of decrease of charge on the capacitor. And of course, charge is proportional to current. So the rate of decrease of the current is going to decrease. And since charge is proportional to current, so the rate of decrease of current decreases as the current decreases. So the rate of decrease of the current the rate of decrease of the current decreases, the rate decreases. Because remember, the rate of decrease is the current. So the rate of decrease of the current decreases as current decreases, giving, I think this shape is exponential, giving an exponential shape. When I say the rate of decrease of charge on the capacitor is proportional to or is equal to the current in the resistor, and charge is proportional to current. So if the rate of decrease of the current decreases, the rate of decrease of the current decreases as the current decrease. So here we are seeing a decrease in current, but the gradient is becoming smaller. So it means the rate of decrease is decreasing. The rate of decrease is decreasing. It is quite abstract. So any of these 3 points, I think, would give you the 3 marks. You don't need to write all of this. Use the figure to determine the resistance R. Of course, we know R could be V over I. So, of course, I know that at T, when T was 0, V was equal to 12 volts. And so this is going to be 12. But what is I? I at T equals to 0 is, so we just read it from here. I think this is 0.13. So it is 0.13 milliamperes. So this will be divided by 0.13 times 10 to the power of minus 3. So 12 divided by 0.13 exponent minus 3. So this is 9.2 times 10 to the power of 4. 9.2 times 10 to the power of 4 ohms. The time constant tau, the time constant. Of course, we know that current is equal to I naught e power negative t over capital tau, where tau is the time constant, which is R times C. So I'll use this. I will use this. So let me say let me check for a simple value of time. Let's say, can I use 4? No, 4 is not very precise. Can I use 6? Let me use this one here. So this is 1, 2, 3, 4, 5. So this is 5. At t equals to 5, what is the current? So this is 0.01234. So this is 0.04. I think that is 0.04. Yeah. So for t equals to 5.0 seconds, I is equal to 0.04 milliamperes. So I'm going to substitute in these two. So I 0.04 should be equal to I naught, which is 0.13, of course. Then times e power negative t. The time is 5, so negative 5 divided by t. I'm introducing ln. So I'll say ln of, I'm dividing both sides, remember, 0.04 divided by 0.13. When I introduce ln to the right hand side, I only remain with the power, so it will be power to be negative 5 over t. So it means t is going to be equal to negative 5 divided by ln of 0.04 divided by 0.13. So I'll start with the denominator, 0. Let me just say ln of 0.04 divided by 0.13. Then I'll say negative 5 divided by the answer. So this is giving me negative 4.2. So this is negative, it's not negative, it is 4.2. So my answer here is going to be 4.2. So depending on the points you choose, your answer will be, the examiner will determine the tolerance, but I think the answer would be between 4.2 or 4.3 seconds. Any of those, 4.2, 4.3 seconds, depending on the value you choose from the graph. The tolerance could be around that value. The examiner determines the tolerance. Use your answers in B to determine the capacitance C. So I'll use my answer, which is 4.2. So we know that the time constant is the product of the resistance and the capacitance. So the capacitance C is going to be 4.2 divided by the resistance C, which is 9.2 times 10 to the power of 4. So 4.2 divided by 9.2 exponent 4. So this is giving me 1, 2, 3, 4, 5, 4.6 times 10 to the power of negative 5. 4.6 times 10 to the power of minus 5. Or you could write this as a 46 times 10 to the power of minus 6, which is 46 microfarads. So I'll just write here 4.6 times 10 to the power of minus 5, or you can write 46 microfarads. Question 7. A circuit contains a power supply that provides a sinusoid alternating input voltage V in. There is an output voltage V out as shown, V out across a load resistor R as shown in the figure. Okay. Set the purpose of the circuit. Let me check. Isn't it this a full wave rectifier? So if this is positive and this is negative, current will flow like this. It won't take this route to enter from this point to the load. Then it will continue. It will take this route and come back here for the first half cycle. So that is positive. For the second half cycle, this becomes positive, negative. So current is now flowing in this direction. Let me change the color. For the second half cycle, this is positive, this is negative. So current is now flowing like this. It will not take this route. It will take this route and it enters from the above. So that means current is always entering from the top. So that means the second half cycle is also positive. So this is going to cause a full wave rectification. So the question is, what is the purpose of the circuit? So I will simply say full wave rectification of the input voltage. Full wave. This is full wave rectification of the input voltage to DC, or direct voltage. You can say direct voltage if you want. Full wave rectification of the input voltage to direct voltage. Let me just put direct voltage, because when I put this, it confuses students. To direct voltage. To direct voltage, because both positive and negative inputs are turned to positive, because both positive and negative inputs are turned to positive. So it is full wave, because both the positive half cycle and the negative half cycle have resulted into positive output. The figure shows the variation of V out with time t. Okay. The load resistance R has a resistance of 370 ohms. Show that the maximum power dissipated in R is 0.22 watts. So if you use the DC value, direct current values, power would be using, because we want to find max, we have the resistance and we have the V from the graph. For DC values, this would be V squared over R. But now that we are looking at alternating values, so this would be maximum, the maximum output, so P naught, the maximum power dissipated P naught is going to be V naught squared over R. So this is going to simply be, from the graph, my V naught is this one, which is, I think this is 9. Yes, that is 9. So this is going to be 9.0 squared divided by R, which is 370. So this is going to be 9 squared divided by 370. So that is 0.2189 recurring. So that is 0.22. So this is 0.22 watts as required. On the figure, sketch the variation with T of the power P dissipated in R. Remember, the output, the maximum power is a constant. So the question is, where do we have maximum power? When do we have maximum power? First of all, let me, from the graph, the scale here is 0.2 divided by 10, which is 0.22. So each small square is 0.02. So 0.22 will be along here. So my graph should not go beyond this point here. But remember, from power equals to V squared, V naught squared over R sine omega t, because it is alternating. Power will be V naught squared over sine. Instantaneous power will be V naught squared over R sine omega t. And actually, this is sine squared omega t. So when t is 0, of course, when t equals to 0, power is going to automatically be 0. So my graph starts from here. When t equals to, is this half a cycle? A full cycle is 0.04. Half a cycle is 0.02. So half a cycle is the same as, okay, the period is 0.04. I just want to show you one example here. If omega is 2 pi over the period, which is 0.04, that is omega. Then if t equals to 0.02, 0.04. That means omega will be sine squared omega t will be the same as sine squared, where there's omega t, I will put 2 pi. Sine of 2 pi, I think that is 0. And what is, if t equals to half a cycle, which is 0.02, so it means sine, this one is 0, sine squared omega t will be sine squared, where there is t, I'm putting 0.02, so it means I remain with pi over 2. So this will be sine pi over 2. And I think sine pi over 2 is also 0. I can check this. Sine of 90. No, sine of 90 is not 0. It's 1. When you square it, it becomes let me first check sine of 2 pi. Sine of 360 is 0. Then sine of 90 is 1. But remember, so sine of 2 pi is going to be 1. This is not V naught, this is V squared. It's instantaneous power. This will be V squared over R sine omega t. So let's substitute values. So at t equals to 0, V was 0. So it automatically means P is 0. Then at t equals 0.02, we are seeing that 0.02 is half a cycle. So it means omega is, remember omega is 2 pi over period. And the period is 0.04. When I put in t, I remain with sine squared pi over 2, which is 1. But remember, V at 0.02 was 0, so the graph here will also be 0. Whenever the V is 0, the graph will go to 0. Then at t equals to a quarter cycle, that is in between here, V was maximum, which was 0.02. And of course, this is always going to be 1. So that means our graph is going to touch this point. This point 1, 2, 3, 4, 5 here. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, so the graph of power is going to be just like this. Okay, so that will be the graph for power. Then calculate the average power. Since we know that the maximum power is 0.22, of course the average power is going to be just the mean power is going to be 0.22 divided by 2, which is going to be 0.11. The average power is half of the peak. The circuit of the figure is disconnected and R is connected directly across the power supply. So we have the power supply and R is connected directly across the power supply. Explain without calculation how the mean power now dissipated in R compares with the answer in B. Of course, even if we don't have rectification, we know that power dissipated is equal to I squared times R. So the power depends on the square of the current. And remember, even if I is equal to I naught sine omega t, so if I square this to be I squared I naught squared sine squared omega t, so even if there is no rectification, I think the graph will have the same shape. So the power is going to be equal to I naught squared R sine squared omega t. So it means the graph will have the same shape because it is depending on this, because this one will be just a half. So I will simply say the mean power is not dependent onto the current, but depends on the square of the current, or it is not dependent on the current direction, because here current can keep changing direction through the resistor, but the average power dissipated will still be there. So I will say the mean power is independent of the current directions since it depends on the current squared. Since it depends on the current squared, so the mean power will be the same, or it will be, you can say, unchanged. And the power time graph will be identical. So the power time graph will be the same as the one we have just we have just seen above. So it will be the same graph as the one we have just drawn above. Okay, so what is meant by a photon? This is, I think, quantum physics. State what is meant by a photon. How many questions were in this paper? Okay. So we know that a photon is a packet, or you can call it a quantum of energy. Of electromagnetic radiation. It's a packet or a quantum of energy of electromagnetic radiation, and of course we know that energy equals to frequency multiplied by Planck's constant. The figure shows a tube in which X-rays are produced at a metal target. Okay. Particles are accelerated from the filament to the target by a constant high voltage applied across the terminals X and Y. State the name of the particles. Of course, these are automatically going to be electrons. Then on the figure 8.1, use plus and minus signs to label the terminals X and Y to indicate the polarity of the high voltage. Of course, the cathode is connected to the negative, so this must be minus. And the anode, the target anode, must be connected to the positive, so it is at a high positive potential, so this is plus. Okay. Then for an accelerating voltage of 32 kilovolts in figure 8.1, determine the maximum energy in mega electron volts of an X-ray photon produced at the target. So of course we know that energy is going to be equal to the charge times the accelerating PD. The charge times accelerating PD. So this is going to be the charge of the electron, because the energy of the electron is what becomes the energy of the X-ray photon. And for a photon to have a maximum energy, it means all the energy of the electron, which is given by the charge times accelerating PD, has become a photon. So this is going to be the charge, which is 1.6 times 10 to the power of minus 19, then times the accelerating PD, which is 32,000. But then they want the answer into mega electron volts. We know that 1 electron volt is 1.6 times 10 to the power of minus 19 joules. And 1 mega electron volt is going to be 1.6 times 10 to the power of minus 13 joules. We multiply by 10 power minus 6. So to bring in mega electron volts here, I'll divide this by 1.6 times 10 to the power of minus 13. Okay, so here the answer is going to be in mega electron volts. So I'll simply say 1.6 exponent minus 19 divided by 1.6 exponent minus 13 times 32,000. So I'm getting 0.032 mega electron volts. The maximum momentum of an X-ray photon produced at the target. Of course, we know that the momentum P of a photon is energy, which energy must be in joules divided by the speed of light. So the energy is, of course, I have to take this back. So the energy is going to be 0.032 times 1.6 times 10 to the power of minus 13 to change it into joules, then divide by 3 times 10 to the power of 8. So I have that times 1.6 exponent minus 13 divided by 3 exponent 8. So I'm getting 1.71 or 1.7 times 10 to the power of minus 23. Then the maximum wavelength of X-rays produced at the target. We also know that energy of an X-ray photon is HF, which is the same as HC divided by wavelength. So the wavelength is going to be HC divided by the energy. So H is 6.63 times 10 to the power of minus 34, 3 times 10 to the power of 8 divided by, because when the energy is maximum, the wavelength is minimum. So this is minimum, this is maximum, because they are inversely proportional. So this is divided by the energy, which is 0.032. But I have to change it to joules. So times 1.6 times 10 to the power of minus 13. So I'll have 6.63 exponent minus 34 times 3 exponent 8 divided by 0.032 times 1.6 exponent minus 13. So I'm getting 3.9 times 10 to the power of minus 11. 3.9 times 10 to the power of minus 11. Explain why X-rays can be used to produce images of internal body structures that have good contrast. When we talk about good contrast, we are actually referring to bone and soft tissue. Why? Because bone and soft tissue have different attenuation coefficients for X-rays, and therefore the absorbed X-rays are different extents, giving a very good contrast. So I'll simply say bone and its surrounding soft tissue soft bone and its surrounding soft tissue have very different linear attenuation or absorption. Linear attenuation coefficients. You know what we mean by attenuation? Loss in signal strength, loss in the strength of the X-rays. So bone and its surroundings of the tissue have very different linear attenuation coefficients, and therefore absorb X-rays to extremely different extents. To extremely different extents. And therefore absorb X-rays to extremely different extents. Hence, transmitted intensities by bone and soft tissues are very different. Hence, because I want more marks, hence, hence, transmitted intensities, those are the intensities which go through bone and soft tissue, hence transmitted intensities. Hence, transmitted intensities by bone and soft tissue are very different, leading to a good contrast. So leading to a good contrast. Okay, let's go to question number 9. Define half-life of a radioactive isotope. Of course, we know that half-life is the time taken for, let's say, the activity of a given sample to reduce to half of its original value. So I'll simply say time taken for the activity of a given sample to reduce to half of its original value. The time taken for the activity of a given sample to reduce to half of its original value is what we call the half-life. You can define this as the time taken for the number of undecayed nuclei in a sample to reduce to half of the original value. Okay. Radioactive isotope X decays to isotope Y. A sample contains only nuclei of X at time t equals to 0. At t equals to 0, we only have X. The figure shows the variation with the t on the numbers of nuclei of Y and of X and Y as the sample decays. So we are even seeing that after decay, we only have X decaying and Y. That means Y is not decaying any further. So it means Y must be a stable isotope. Okay. State the name of the quantity represented by the magnitude of the gradient of line X. So we have a graph of number of nuclei against T. And the gradient is going to be the change in the number of nuclei divided by the change in T. This is the number of nuclei decaying per unit time is the same as activity. So this is going to be simply activity of X at time T. So that is simply going to be the activity because the gradient is changing n, that is the number of nuclei decaying, over the change in time. So that is the same as the rate of decay, that is activity. Then state 3 conclusions about X or Y that may be drawn. It is either X or Y that may be drawn from the figure. The conclusions may be qualitative, that means you can give a number, or quantitative, just an explanation. Use the space below for any working. I've already mentioned one because we are always seeing X and Y. The first thing I will mention that is that Y is a stable. Y is a stable isotope as no further decay is seen, as no further decay is seen. Y is not decaying any further, so it is a stable isotope. I just want to put this in brackets because even if I don't give it, I still have the mark, as no further decay is seen. So Y is a stable isotope. So from the graph, I'm now going to do a few calculations. Let me first find the decay constant. Or let me check the half-life first because it's easier to see. So where these ones meet, this is the half-life. Oh, I divide 4 by 2. I get this. So the half-life is here in this box. Okay. So the scale is 10 divided by 10, which is 1. So 11, 12, 13. So this is approximately 13. Let me see. It is approximately 13.5. It is very close to the right hand side and to the left. So it's about 13.6 seconds. It's somehow to the left of the center. So it is approximately 13.6, but I think the examiner may accept 13.5. Alternatively, I can try the second point. When I divide this by 2 again, I reach 1. And it is here. Okay, let me try the third time. Divide by 2, I reach 0.5. It is here. So this is 41. So that is the third half-life. 41, let me check. 41 divided by 3. 41 divided by 3. Yes. 13.6, 13.7. 1, 2, 3, 4, 5. So it can't be 13 point. If you say this is 13.5, 13.4, 13.6, then the answer is approximately 13.6. So I'll take 13.6. So one was that. Number 2, I'll say the half-life. Half-life of X is 13.6 seconds. So if I have the half-life, I can predict the decay constant. Lambda is going to be ln of 2 divided by t a half. So it is ln of 2 divided by 13.6. ln of 2 divided by 13.6. That is 0.051. So the decay constant is 0.0. I'm not following the numbering. Decay constant equals to 0.051 second. It is per second, of course. This one is per second, not seconds. That is number 2. Then number 3. Number 4. Let me try to establish the activity maybe at t equals to 0. So we know that activity is equal to A naught times, okay, the activity at t equals to 0, I'll call it A naught. And A naught is going to be equal to wavelength, decay constant times N naught. And the decay constant we have already seen is 0.051 times N naught. Let's check N naught. Let's check N naught from the graph. N naught is 4. At equals to N naught is 4 times 10 to the power of 22. So this is going to be times 4 times 10 to the power of 22. What is the initial activity? 0.51. Sorry. 0.051 times 4 exponent 22. So it's 2.0 times 10 to the power of 21 becquerels. So the initial activity or activity of X at t equals to 0 seconds is 2.0 times 10 to the power of 21 becquerels. What else can I find from here? I think the total number of nuclei from the graph is constant because we see the number of nuclei of X decreases up to around here, and the number of nuclei for Y, this is, what is this? I think this raises to up to 3.8? No, 3.8, yes. And this falls from 4 to 0.2. So you notice that the difference is the same. 4 minus 0.2 is 3.8. So it means the number of nuclei is constant. Total number of nuclei is constant. So I'll say total number of nuclei is constant. That is, I think it is 3.8 times 10 to the power of 22. Total number of nuclei is constant from the graph. What have I left out? I think I can also talk about the amount of X. That is the number of moles, maybe. Let me check amount. Amount, number of moles is equal to, remember, mass over the molar mass, which is the same as number of nuclei divided by Avogadro's number. So I'm finding amount at t equals to 0. So this is going to be 4 times 10 to the power of 22 divided by Avogadro's number, which is 6.02 times 10 to the power of 23. 4 exponent 22 divided by 6.02 exponent 23. So it is 0.066. 0.066 mole. So it means I will say the last one. I think this should be the last one. Amount of X at t equals to 0 seconds is 0.066 mole. Is it 0.066? Yes. Okay, so you can mention any three of those six. The mass of a radioactive isotope X in the sample in B is 7.3 times 10 to the power of minus 4 kilograms. At T equals to 0, determine the nuclear number of isotope X. So, of course, we know that the number of moles equals to the mass over molar mass, which is the same as number of nuclei over Avogadro's number. But of course, we know that the number of the nuclear number is the same as the mass in grams. So I will simply say nuclear number is the same as the molar mass in grams. So I must ensure that my final answer is converted into grams. So I will simply say the molar mass. I will make the molar mass the subject, mR molar mass. The subject will be N over Na times M. So N was, I think N is the mass of the radioactive is that. So did I make M correctly? No. This is wrong mathematics. So this is going to be Avogadro's number, Na over number of molecules, then times small m. I think that is correct math. So this will be 6.02 times 10 to the power of 23 divided by capital N, which I think was 4, times 10 to the power of, because this was at t equals to 0, so the power of 22, times 7.3 times 10 to the power of minus 4. This is still in kilograms, but I must change it to grams later on. So I'll press my calculator. 6.02 exponent 23 divided by 4 exponent 22. Then I'll multiply this by 7.3 exponent minus 4. So this is 0.0109865 in kilograms, which is the same as, I'll multiply this by 1,000 to change it to grams. 10.9 or approximately 11. 10.9865 grams, which is approximately 11. So the answer is going to be 11. Okay, lastly, I think I've used more time, but it's because I give a lot of explanation. State what is meant by luminosity of a star. Of course, this is the total radiant power. Total radiant power emitted by the star. That's what we call luminosity, total radiant power emitted by the star. Explain how a standard candle in a distant galaxy can be used to determine the distance of the galaxy from an observer. Of course, the distance is got from F equals to L over 4 pi d squared. For a standard candle, L is known. What the examiner needs to do is to measure F. And when F is measured, the radiant flux intensity is determined, and L is known, then D can be obtained from that formula. So I will simply say a standard candle is an astronomical object which has known luminosity. I'll put L in brackets. So the observer measures the radiant flux intensity received The observer measures the radiant flux intensity F received, and the distance is calculated, and the distance D, I want to put a D here, and the distance D is calculated from F equals to L divided by 4 pi d squared. As simple as that. The Sun has a radius of 6.96 times 10 to the power of 80 meters and a surface temperature of 5780 Kelvin. Light from the Sun is observed to have a peak intensity at a wavelength of this. Capture the luminosity of the Sun, give a unit with your answer. So we know that the luminosity L is also equal to 4 pi times, it's 4 pi times sigma times r squared times t to the power of 4. So this equation is given in the list of formula. So I'll just substitute. This will be 4 pi. Sigma is Stefan Boltzmann's constant, which is 5.67 times 10 to the power of minus 8. It is given in the list of constants, sigma. Then the radius has been given as 6.96 times 10 to the power of 8, but this is squared. Then times temperature, which is 5780 power 4. So I have 4 pi times 5.67 exponent minus 8. Then times 6.96 exponent 8, but this should be squared. Then times, I have to say 5780 power. So I have to change this to power 4. So it's 3.85 times 10 to the power of 26. Since they have given us R to 3 significant figures, I will not write to less than 3 significant figures. All the quantities given here are up to 3 significant figures. So I'll write this as 3.85 times 10 to the power of 26. Of course, luminosity is measured in watts. Another star emits radiation that has a peak intensity at a wavelength of 624 nanometers, determine the surface temperature. So here I'll use Wien's displacement law, which states that lambda max, that is the wavelength at which maximum intensity occurs, is inversely proportional to temperature. So lambda max times T should be equal to a constant. So for the first one, I had 501 nanometers as wavelength times the temperature was 5780. Since it is a constant, should be equal to the second one, which is 624 nanometers times the temperature, which is not known. So the units of nanometers have cancelled out. We only remain with the units of Kelvin. So T is going to be equal to 501 divided by 624, then times 5780. I write my answer to 3 significant figures strictly, or more, not less, because all quantities here are 3 significant figures. So I'll have 501 divided by 624 times 5780. So that is 4640. So this is 4640. Kelvin. If you write 4600, you may not get the mark. Yeah, I think I've used 10 extra minutes to finish this paper. The rest are blank pages. Thank you for watching this video. I hope you have learned something. Until next time, bye bye.